español. Y bueno, empieza a escuchar.
So most of the papers, the talks that you will hear at this conference have to do with innovations in science and engineering, things that are going on today and that will be going on in the near future. My talk this morning will be primarily historical in nature. I want to talk about the things that have happened over about 100 years after Professor Albert Einstein published his theory of general relativity. Up until a few years ago, my colleague over here and some others discovered gravitational radiation directly with instruments built here on Earth.
So, muchas de las charlas que van a escuchar en estas 10 conferencias están relacionadas con ciencia, ingeniería, mucha innovación. La charla de él va a tratar sobre descubrimientos físicos que han tomado aproximadamente 100 años, ¿no? Desde la creación de la teoría de la relatividad de Albert Einstein.
So here is a brief overview of the topics that I want to cover. Relativity was published in 1915. The first experimental test of this theory, a theory of gravitation, was done just a few years later in 1919. Following that time, there was considerable discussion about whether a phenomenon known as gravitational waves, which appears to be required by relativity theory, whether that actual phenomenon could be observed. That was in some question, and it was discussed at considerable length during those few years.
So, los temas que se van a presentar son la teoría de la relatividad que aproximadamente entre 1905 y 1915 fue propuesta por Albert Einstein. También el concepto de las ondas gravitacionales que demoró un buen tiempo, ¿no? en discutirlas, pueden ver de 1920 a 1960 aproximadamente.
Now my own work comes into this discussion because of the discovery of an astrophysical phenomenon known as pulsars. They were discovered in 1968 and much work was done to try to establish how these special kind of stars, neutron stars, fit into the general scheme of stellar evolution, the evolution of other kinds of stars and material in the universe. It happened that one discovery made by a man who was then my student and I in 1974, a so-called binary pulsar, enabled us to make very precise tests of relativity theory. And that was a new test that enabled us to make sure that, at least as far as we could tell from that experiment, gravitational waves do in fact exist. And of course that gave rise to the ability to fund the very large experiment which resulted in the detection of gravitational waves directly. This instrument known as LIGO and its sister instrument Virgo in Europe were built starting in the late 1980s.
So, lo que van a escuchar en esta charla es el trabajo que inició él sobre el estudio de los pulsares aproximadamente en 1968 hasta 1974, que permitió probar o verificar los conceptos de teoría de la relatividad de Albert Einstein y también, ¿no? La detección de las ondas gravitacionales, y que ese trabajo ha permitido, ¿no? Detectar las ondas gravitacionales el año pasado, ¿no? hace un año, ¿no? Que se descubrieron con el experimento LIGO.
Some of you may remember that there was a news release made just about 2 years ago now, in February of 2016, announcing that gravitational radiation, gravitational waves had been discovered, had been detected directly 100 years after Einstein's theory predicted them. For example, the newspaper headlines in English read something like, LIGO, the name of the instrument, opens a new window on the universe. With observation of gravitational waves and so forth. These were in newspapers all over the world at that time.
Lo que se vio mucho en las noticias el 2016, fueron titulares como lo que presentan acá, ¿no? La detección de las ondas gravitacionales observadas a 100 años después de la predicción de Einstein. Digo, que es el tema que les mencioné, abre una nueva ventana al estudio del universo con la observación de estas ondas gravitacionales debido al choque de agujeros negros.
So here is the young Albert Einstein in 1905. At this point, he is about 25 years old. He's working in the Swiss Patent Office. Here he is just a few years later, in 1912, when he's working on the general theory of relativity.
Y pueden ver a Albert Einstein, bastante jovencito, de unos 25 años, era empleado en una oficina de patente, trabajando en los temas de la teoría de la relatividad.
So one of the original predictions of this theory of gravitation was that starlight should be bent by a small amount when it passes by another massive object. For example, when the light of a star passes by the sun, it will appear to be deflected by a small angle, and the star will appear to be at a slightly different place in the sky. Now, of course, when the sun is out, you can't see stars. But during an eclipse of the sun, when the moon passes in front of the sun is, of course, blotted out, and you can see the stars behind. So there was a specific prediction that one should be able to observe small displacements of the positions of stars in the sky during a solar eclipse.
Uno de los temas que predice la teoría de la relatividad es la curvatura o la doblez de la luz cuando atraviesa un objeto masivo. Obviamente que esto es difícil de observar porque cuando está el sol no se pueden ver las estrellas, pero se puede estudiarlo, se puede observar este fenómeno cuando hay un eclipse, ¿no? Cuando la luna está enfrente del sol.
So here is in fact the picture taken by the English eclipse expedition in 1919 attempting to observe this phenomenon. This is a picture of the sky during the solar eclipse. It is a negative picture so that things here which look bright are actually dark, things that are dark are actually bright.
So, acá pueden ver una figura del eclipse solar de 1919 por Edison. La imagen es opuesta a lo que ustedes observan, lo que es blanco debe ser negro, lo que es negro es blanco.
And here is some little marks to indicate the positions of stars which have been deflected by very small amounts during the passage of the sun along the path. And according to the prediction of relativity, the stars were in fact observed to be deflected by the same small amounts as predicted by the theory.
Acá pueden ver los círculos rojos que son posiciones de estrellas y que han sido, la luz ha sido doblada, ¿no? Debido a la masa del Sol. Y que obviamente esto fue una predicción de la teoría de la relatividad.
As it happens, it was not a very precise experiment, but it did show that the bending of light predicted by Einstein in fact does occur, and it made Einstein famous overnight. Newspaper headlines, again, all over the world, some of them said strange things like the lights are all askew in the heavens, and you know, but in any case, it was clear that Einstein had a major triumph, and not very many years later, he was honored by the Nobel Prize in 1921. In fact, the prize was awarded for another paper of Einstein's that had nothing to do with relativity, but everybody knows that part of the major reason for his fame was owing to a number of different major scientific contributions that he made in those early years.
El experimento en sí no fue, digamos, muy completo, muy preciso, pero los titulares de los periódicos en aquella época indicaban, ¿no? Que las observaciones de este eclipse probaban, ¿no? Lo que Albert Einstein había dicho con su teoría, y esto permite que se vuelva famoso de un día para otro. Titulares de 1919 que les los mostró hace un momento. En resumen, Albert Einstein se vuelve famoso de un día al otro. y pocos años después consigue el premio Nobel, pero este premio Nobel que le dan a Albert Einstein no es por la teoría de la relatividad, sino por otro fenómeno que no está relacionado. Pero Albert Einstein a través de los años ha hecho muchas contribuciones importantes en el mundo científico, ¿no? Y acá está el premio Nobel de Física en 1921 para Albert Einstein.
And as it happens, this precise description of gravitation has been so important that it has, in later years, led to 2 additional Nobel Prizes, which you will hear about as we proceed during these next few minutes. So the equations of Einstein's theory, general relativity, have wave-like solutions. Gravitation propagates from one place to another, in part by means of waves when masses are accelerated rapidly. And many questions arise very naturally to a physicist discussing this phenomenon. Are these wave solutions physically meaningful? Is there something that we could calculate that would tell us the speed of these waves, the energy that they carry? Could these waves possibly be detected? All of those things were clearly of interest, although the answers to those questions were not known at the time.
Los conceptos en las ecuaciones de la teoría de la relatividad proporcionan soluciones a esas ecuaciones que son tipo de ondas, como generan una serie de preguntas muy importantes, como por ejemplo cuando un físico analiza un resultado de una ecuación, lo primero que se pregunta es si es que estas soluciones de ondas son físicamente posibles. También si podemos calcular la velocidad, la energía de estas ondas, ¿no? Y lo otro que también es importante es si es que se pueden detectar estas ondas.
The question of whether these waves were real was scientifically very important at the time, and there was much writing about it. Questions about whether the waves actually were required by the theory was not very clear, and a number of things like the ones that I have quoted on this slide appeared in the scientific literature at the time. There are no gravitational waves. Plane waves traveling along the x-axis can be found, so they do exist. Gravitational waves do not exist, so maybe yes, maybe no. We're not sure. Do they exist? Maybe you can say a few of those things. It's not clear.
En ciencia muchas veces uno encuentra soluciones, y vuelvo a reiterar, ¿no? Cuando uno resuelve una ecuación matemática, uno tiene que interpretar cuidadosamente la solución para ver si tiene significado físico, ¿no? Y acá hay una serie de frases o extractos de aquellas preguntas que se hacían en la época. Lo primero es, ¿existen las ondas gravitacionales en sí que producen la ecuación de la teoría de Albert Einstein? Las ondas gravitacionales son simplemente ondas planas que viajan en una dirección X y pueden ser detectadas. Luego otro comentario que dice no, las ondas gravitacionales no existen. Luego la pregunta nuevamente de ¿en verdad existen las ondas gravitacionales? En fin, hay que hacer un método riguroso y ese era el tema de debate de la época.
And the important thing that I want to emphasize is that all of these statements were made by Einstein himself. So he's not sure. Yes or no, we're not sure.
Lo gracioso es que todos estos extractos y comentarios que les acabo de mencionar fueron hechos por el mismo Albert Einstein.
So there were a number of papers published in these years, and he's discussing the question with himself, basically. Do gravitational waves exist in the general theory of relativity? And others also weighed in on the questions. Professor Eddington from the UK was one of those who early on contributed to the theory, and he concluded that the correct answer was yes, gravitational waves do exist. But then Einstein, again, a few years later, in the 1930s, wrote a paper together with a collaborator named Nathan Rosen, in which they concluded that gravitational waves do not exist. And I want to, because it's an amusing story, I want to lead you through a little bit of the discussion of this conclusion that Einstein reached in 1936.
A través de esos comentarios que presentamos hace un momento, Albert Einstein produjo una serie de papers donde él mismo discutía y se respondía a sí mismo con esta serie de papers sobre si estas ondas gravitacionales existían o no. El colega Eddington en 1994 le dice que sí existen, que las ondas gravitacionales existen, y hay un paper escrito por el mismo Albert Einstein y otro colega Rosen en 1936 en que ellos concluyen que no existen, y luego que sí existen, y bueno, la pregunta es confusa, ¿no? Y justamente en la charla de hoy él intenta llevarles por ese viaje para ver y tratar de entender, ¿no?, el tema de las ondas gravitacionales.
Now, I point out that we know the story that I'm about to tell you in part because of the painstaking work of a very excellent young historian of science named Daniel Kennefick, who has written a book that if you enjoy reading this sort of thing in English, it's called Traveling at the Speed of Thought. He's basically examining the history of understanding of gravitational radiation. So, Einstein, it turns out, we know many of his letters are still in existence. We have copies of them. He wrote a letter in 1936 to his friend Max Born, another German physicist. They had both escaped from Nazi Germany during the 1930s. Born was in the United Kingdom. Einstein, by this time, was in Princeton, New Jersey, in my hometown. And Einstein writes to his friend Born, together with a young collaborator, that's Mr. Rosen, I have arrived at the interesting result that gravitational waves do not exist, though they had been assumed a certainty to the first approximation. So.
Hay un trabajo en un libro por el profesor de la Universidad de Arkansas, Daniel Kennefick, escrito un libro que se llama Viajando a la velocidad del pensamiento, que documenta esta historia de las ondas gravitacionales. El mismo Albert Einstein escribe una carta a su colega Max Born, ambos escaparon de la Alemania nazi en 1936, en el que le dice, ¿no?, junto a un joven colaborador llegué al resultado interesante de que las ondas gravitacionales no existen, aunque se asumieron con certeza como una primera aproximación.
So Einstein and his collaborator Rosen submit the paper to the American Physics Journal known as the Physical Review. The Physical Review today is the most prestigious journal in all of physics, probably. At the time, it was a fairly young publication, and its editor was trying to make it into an important worldwide review of physics progress in science. Anyway, they send their paper to the Physical Review, and it is taken into consideration by the editor of the journal, whose name is John Tate. His policy was to send papers to another physicist to be reviewed and to consider whether the paper is correct. This was a policy that is now used in almost all scientific literature, but at the time, in the 1930s, was not widely used in Europe.
En 1936, Albert Einstein y su colega Rosen envía un artículo, ¿no?, científico a la revista Physical Review, que hoy en día es la más prestigiosa en física, sobre el tema de las ondas gravitacionales. El editor era John Tate, y lo que él hace es enviar el artículo a un referí para que revise. No, es una práctica que hoy en día se hace para publicar manuscritos científicos, pero en la época no era una práctica, digamos, muy común.
So Tate writes a short letter to the person who is going to do the reviewing and says, I would be glad to have your reaction, and the review sends back his review to Tate. I want to read for you just a few comments that were made by the referee. He says, well, I have studied the paper carefully, and I don't believe that Einstein and Rosen have established their case. It would be very important if they have, but I think they have made some mistakes, and he points out what some of the mistakes are, and he conveys this information back to the editor, Mr. Tate. So Tate at this, well, I'll let you review that quickly.
Okay.
Yeah.
So, el paper se lo envía el editor John Tate, quien lo envía a un referí, como mencioné, para que evalúe, ¿no?, la calidad del manuscrito. El referí le devuelve el manuscrito con muchos comentarios y errores, ¿no?, para que lo vuelvan a considerar.
So the editor writes back to Professor Einstein and says, we would be glad to have your reaction to the various comments and criticisms that the referee has made.
El editor John Tate escribe a Albert Einstein en la época y le dice, me daría muchísimo gusto saber su reacción a los diversos comentarios y críticas que el referee ha indicado.
Einstein is not accustomed to having people criticize his work. And so he writes a letter back immediately to the editor, and here it is in handwriting. It's written in German. I do not read German very well, and I'm sure you can't read it from here. But here is what he says in English, and I'll let Julio Urbina repeat it for you. He says, we had sent you our manuscript for publication and had not authorized you to show it to specialists before it is printed. And he goes on to say, I see no reason to address the, in any case, erroneous comments of your anonymous expert. On the basis of this incident, I prefer to publish the paper elsewhere. All right?
Nosotros, el señor Rosen y yo, le hemos enviado nuestro manuscrito para que lo publique y no le habíamos utilizado para que le muestre a especialistas antes de ser impreso. No veo razón alguna para contestar sus comentarios, en todo caso errado, los comentarios de su experto anónimo. Debido a ese incidente, prefiero publicarlo en otro lugar. Como menciona, Einstein era muy bueno tomando críticas, ¿no?
So for many years after this, Einstein did not send any more papers to the physical review. He did not like that treatment.
No le gustó enviar artículos por muchos años al Physical Review.
So this man is the referee. He is the person to whom the paper was sent for criticism and pointed out the errors in it. His name is Howard Robertson. He was a mathematical physicist at my university, Princeton University. And in 1937, in February, he writes another letter back to the editor of the journal in which he says, you neglected to keep me informed on the paper submitted last summer by your most distinguished contributor. That was Einstein's paper. But I shall nevertheless let you in on the subsequent history. The paper was sent without even the correction of the 1 or 2 numerical errors that I had pointed out. It was sent to another journal, and when it came back in galley proofs, it was completely revised because I had been able to convince him in the meantime that it proved the opposite of what he thought. Okay, so you can just summarize the end of that.
Acá está una foto de ese referí que le envió los comentarios al paper de Einstein, 1937, en el que le escribe nuevamente al editor John Tate de Physical Review diciendo de que se ha olvidado de mantenerlo al día de esta publicación y que se ha enterado que ha sido publicado en otro medio y que efectivamente, ¿no?, este otro medio tiene las correcciones que él había indicado.
So, well, here is Einstein in 1937 in his office in the Princeton Institute for Advanced Study. I think perhaps he's thinking about, did I make a mistake? Did I not make a mistake? You know? Anyway, Robertson has pointed out that he has made a mistake, and the paper is published in another journal, and at the end of the paper, there is a note added to the paper that basically says the paper was significantly revised because we had interpreted our formula results incorrectly, and he thanks Professor Robertson for his assistance in the clarification of the error. Now, Einstein is in one building in Princeton University, and Robertson, the referee, is in another building. So they actually talk to each other, and Robertson persuades Einstein that he had made a mistake.
En la foto anterior muestra a Albert Einstein en el Instituto para Estudios Avanzados en Princeton, tal vez reflexionando sobre la existencia de existe o no existe en la zona. En el paper,
Go ahead.
Fue finalmente traducido y se agregó una nota al final del paper que dice que la segunda parte de este documento fue considerablemente modificado por mí después de la partida del señor Rosen hacia Rusia, que originalmente habíamos interpretado los resultados de nuestra fórmula erróneamente. Deseo expresar mi agradecimiento a su colega profesor Robertson por su amable ayuda en la aclaración e indicación del error. Lo que menciona es que Robertson, el otro profesor, trabajaba en Princeton, en otro edificio, y habían obviamente conversado con él sobre el tema y lo persuadió de que había cometido un error.
So we're changing topics here into something rather different, which has to do with the same development of the same story, of course. During the 1900s, we, that is science in general, learned a great deal more about the structure of matter. We understood the interior of the atom to a significantly higher extent than had been done before. The particle known as the neutron was discovered in 1932, and very shortly after that discovery, it was determined that in a paper by Walter Baade and Fritz Zwicky that a type of star might exist that would be made primarily of neutrons rather than of ordinary atomic matter. That was basically a prediction at that time, but they thought it might have to do with the phenomenon known as a supernova explosion, in which a star explodes and leaves behind a neutron star. That prediction was made in 1934.
So, otro tema, un tema distinto que estamos hablando ahora es las estrellas de neutrón. En 1962 se hizo el descubrimiento del neutrón y se empezó a observar, tal vez con datos, ¿no?, la presencia o transición de las supernovas, que básicamente es la transición de una nueva estrella a una estrella de neutrón.
There was further progress made at about that time in the late 1930s, but as you know, at this time the world was very unstable, and particularly in Europe, things were looking as though war was on the horizon, and pretty soon all of this kind of science had to stop. And of course we went through a terrible period of warfare. And so the story does not pick up again until significantly after the war, into the late 1950s, when things are becoming more normal again. And at that time came the discovery of this phenomenon known as pulsars.
So, sí, hubo cierto progreso al finales de los años 30, pero no mucho, debido a la Segunda Guerra Mundial. Pasaron muchos años y el tema recién se retoma en los 60, y esto llega, ¿no?, al tema de los pulsares.
So the first pulsar was discovered in the end of 1967. It happened that was just at the time that I was finishing my own PhD studies. I had finished writing my thesis and turned it in. I defended my thesis. I was looking for something new to work on, and I thought, this sounds like an interesting project. I will go and do some observations of these objects that came to be called pulsars.
So, en 1967 el tema de los pulsares se descubrió. En la época él era estudiante, el tema que le interesó, había defendido su tesis y bueno, estaba buscando, ¿no?, qué otro tema podría ser interesante para investigar.
So here is an astronomical photograph of a supernova remnant. It is the gas left over after a star has exploded. And near the center, there's one object, a star, which is a pulsar. It rotates rapidly, and it generates broad bandwidth radio frequency noise that can be beamed outward along directions like this. And as the star swings around, that beam is swept across the sky, so that a radio telescope, such as the one in Puerto Rico, where I've done many of my own studies, can pick up the radio noise. These objects are very precise clocks, if you like, because they keep time owing to the rotation of the star.
La foto anterior, bueno, la foto que mostré inicialmente es la nebula del Cangrejo, donde muestra la explosión de una supernova. al explotar estos elementos, generan un campo y una radiación inmensa, ¿no? Y que pueden ser detectadas por estos telescopios, como por ejemplo el que existe en Puerto Rico.
So about the end of the 1960s and into the early 1970s, there were many surveys made with radio telescopes attempting to find additional examples of these pulsar objects. And one of these surveys was the one that I began with my student, Russell Hulse, starting in about at the end of 1972, where we used the large radio telescope near the city of Arecibo in Puerto Rico.
Un poquito de la historia de los pulsares, ¿no? A finales de 1960, principios del 70, se empieza a hacer una búsqueda, ¿no? De si es que existen más pulsares de esta naturaleza. Su trabajo de él en 1972 a 73 que los inicia con su estudiante John Hulse.
So one additional photograph of the telescope here with the material that's up in the air that allows the machine to be steered to different directions in the sky. And here is the student, Russell Hulse, operating the computer. At that time, this was called a mini computer. It's actually very big. This was, of course, in the early days of computing technology. But we had a method in which we could use this mini computer to analyze the information coming into the radio telescope and help us to discover new examples of these objects known as pulsars.
Las tres fotos que mostró anteriormente, las dos primeras son las fotos del radioobservatorio de Arecibo. Y una indicación, el radioobservatorio de Arecibo hace investigación en forma activa y también hace investigación en forma pasiva, y la antena escucha, ¿no?
So within 2 years, we had found a large number of pulsars. We found 40 new ones. But most importantly was one of these objects, which was a binary pulsar, that is, a pulsar in an orbit around another star. So two stars going around each other with high velocities, and this causes the pulses to be Doppler shifted, so that sometimes they're a little bit closer together, sometimes a little farther apart. We can measure from the Doppler shifts the velocities of the pulsar in the orbit, and here is the shape of the so-called velocity curve of this particular binary pulsar. Sometimes it's moving away from us, sometimes it's moving very rapidly toward us.
Un poquito de historia, en 1974, la anterior diapositiva, se detectan aproximadamente 40 pulsares nuevos. Lo más importante de esta secuencia es los pulsares binarios, que son dos ondas que circulan y generan una órbita entre las dos, y el movimiento de estas estrellas se pueden detectar por el efecto Doppler, ¿no? En la figura se ve el acercamiento o el alejamiento, ¿no? de la posición de estas estrellas por el efecto Doppler.
Now, we recognize that this was a unique object. Nothing like it had ever been found before. And it was likely that we could use the Doppler shift measurements to make very precise, detailed examinations of the gravitational interaction between the two stars. In effect, we could test relativity theory in ways that it had never been tested before. And in particular, we should expect that gravitational waves should be generated by this binary pulsar system. That should cause the energy of the orbit to be gradually carried away in the form of these waves, and the size of the orbit should gradually get smaller. The two stars should come closer together.
Una observación sumamente importante de este efecto Doppler es que se pudo utilizar, se dieron cuenta de que esas mediciones podían ser utilizadas para hacer precisiones muy buenas y que verificarían la teoría de la relatividad, ¿no? Y otro aspecto importante es que se podía estudiar la generación de ondas gravitacionales, ¿no?
Now, you'll remember that the details of exactly what the theory predicts were not yet very well determined. There was, in particular, a controversy that had come to be called the quadrupole formula controversy, whether it does or does not correctly exemplify what the general relativity theory predicts in the rate of change of the size of the orbit. There are a number of contributions that have been made to this over the years, but at the time we were doing these measurements in the middle 1970s, the story was not yet agreed upon by all physicists.
So, había una controversia en la época, mediados de los 70, un concepto llamado la forma del cuadrupolo. No se entendía muy bien y había mucho más que explorar.
So let me show you briefly some of the measurements that we are making during this experiment. The picture here, time is on this axis and the year is on the axis down below. And we see that the star is beginning to reach its completed orbit a little bit earlier after a few years than it would have been if the orbit had remained the same speed. This is the decay of the orbit that the theory predicts. And we thought that within a few years, from 1975 up until maybe 1978, we were just beginning to see a little bit of change that would be the confirmation that gravitational waves are actually carrying energy away from this system.
So, acá en esta figura se puede ver la predicción de la órbita y se ve que la órbita completa su ciclo un poquito más temprano de lo que se espera. Se pueden ver ciertas perturbaciones y que, da una impresión de que se podía probar no la existencia de la zona gravitacional.
Now, as time goes on, we would expect the effect to get larger. And in fact, it does get larger. So after a few years, we see a bigger effect. Here it is magnified. We see that by about 1982, we're beginning to see a very clear curvature of that curve. And that helped to make it very important to do the calculation from the theory, again, as precisely as possible to agree upon the result. And it turns out that with this impetus, physical theorists were able to work out that the quadrupole formula does, in fact, give the correct result for general relativity.
Las figuras que mostró, se hacen más mediciones y se encuentra una precisión mejor. En 1982 mostró la figura con esa precisión, lo cual que estas observaciones permitieron a los físicos teóricos en sí verificar que esta forma de cuadrupolo era posible.
So let me just go through this one more time. Here is the beginning of the effect. It's getting a little larger. It's getting a little larger with time. Here it is in in 1992 or so, 1993. The effect is getting very large. It is an easy to measure effect. The orbit actually is getting smaller, and it is doing so at just the rate expected according to general relativity theory. And in fact, the consequence of that experiment showed that gravitational waves clearly do exist and that they behave as relativity says they should. And this, of course, led to another Nobel Prize in which I and my student at the time, Hulse, were honored by the Swedish Academy. A wonderful honor, as you surely know. Let me now skip to, again, yet another new topic and talk just a little bit about the things that you've already heard some about earlier this morning in the talk about the experiment called LIGO and Virgo collaboration. So in about 1990, around the time that we just finished discussing, there had already been a proposal to the American National Science Foundation to build a very large instrument known as the Laser Interferometer Gravitational Wave Observatory, LIGO for short. This was going to be a very expensive project, several hundreds of millions of dollars. And the fact that the binary pulsar experiment showed that the ultimate goal of this other experiment probably was achievable, I think led to the funding being acceptable to the US government.
para comentar los trabajos que él hizo, continuó con las mediciones y comprobó los efectos de la teoría de la relatividad, y los resultados fueron muy buenos, muy precisos, y lo que le permitió conseguir el premio Nobel en 1993 junto con su alumno. Debido a esa, digamos, iniciativa que también predecía o decía que si era posible evitar las ondas gravitacionales, se permite el financiamiento de la Fundación Nacional de Ciencias de Estados Unidos para iniciar investigaciones en el estudio de las ondas gravitacionales.
So the idea of the LIGO and Virgo experiment is that massive objects, such as a pair of stars in an orbit around one another, should generate gravitational waves. They are very weak. They can travel great distances, but they will cause only very small effects at the far end of a great distance. Nevertheless, the ambitious plans of the LIGO-Virgo collaboration on both sides of the Atlantic were to build instruments which they hoped would be able to detect these waves. The two LIGO instruments are in the city of Livingston in the state of Louisiana, and in the near the town of Hanford in the state of Washington. And these instruments involve large, long paths that you can see going out to the sides. Those are evacuated tubes with laser beams shining down them, and the idea is to measure the small deflections of masses at the ends of the tubes caused by the passing gravitational wave. And I think already probably this morning you heard something similar to what I will show you, but in this graph, again, we have the frequency of the gravitational wave and time in seconds, and if we start this up, I hope we will see the signal. That brief signal is exactly what was observed by the LIGO detectors in September of 2015 when they first detected gravitational waves that led to the excitement outlined in the newspaper headlines that I showed you at the very beginning. Here again is the signal, the actual gravitational wave as these two objects come closer and closer together and finally merge into one. And it turns out that the two objects in this case are not stars, but even more massive objects known as black holes. And we know now from the analysis of the shapes of those waves that the two massive black holes started out with masses something like 36 times the mass of the sun, 29 times the mass of the sun, leaving together an object of 62. You might see that that's not the same as the sum. 3 solar masses of material has disappeared and been carried away as energy in the form of the gravitational waves. This whole system was some 1.3 billion light years away from Earth. So we're observing something on the far side of the universe.
La predicción la detección de las ondas de gravedad básicamente era ver si es que el choque masivo, ¿no?, de dos cuerpos podían generar perturbaciones a la gravedad. Pero estas perturbaciones eran pequeñitas, ¿no?, bien chiquitas. Mostró las figuras de los detectores de Virgo en dos ciudades en Estados Unidos, y también mostró las detecciones de estas ondas gravitacionales, ¿no?, en las figuras que mostró. Lo importante es que no eran básicamente estrellas, sino eran agujeros negros con masas, una de ellas con una masa de 36 veces la masa del Sol, la otra con 29 veces la masa del Sol, y la masa final que se detectó debe ser 62 masas del Sol, pero si ustedes hacen la matemática ven que hay una falta de masa, una diferencia de masa de 3 masas del Sol. No, la distancia en la que se estima estas condiciones es aproximadamente 1.3 billones años luz. Indica que está, ¿no?, al borde del universo.
Now, this LIGO experiment took a total time of nearly 50 years. The first ideas for building what became LIGO were obtained in the early 1970s, even the late 1960s. The ideas were being discussed. And here are a couple of the principles. This is Professor Weiss, then a young man at MIT, just beginning his professional career. This man is Kip Thorne at the California Institute of Technology. He had finished his degree at my university, Princeton, and is now studying and teaching at Caltech. This again is in the early 1970s. This man's name is Ronald Drever. He was a Scottish physicist who was talked into working together with the Caltech group and made major contributions to the LIGO project. And here are two of the men, Thorne and Weiss, about 45 years later, at the time that the experiment finally succeeded in making the detection. And a third man, whose name is Barry Barish, another professor at the California Institute of Technology. Barish took a major role in transforming what originally was a small laboratory experiment into a worldwide collaboration, including the Virgo team, and had a major part in making the overall experiment a success. And of course, as you know, if you've paid attention to this kind of scientific news, just a little over a month ago, this team of three people was again honored with a Nobel Prize in December of 2017. Sadly, Professor Drever had died already, but it was nice that the other three were honored in this way. Well, that is the story that I wanted to bring you this morning. An interesting thing that I know there are students in the room. It will be perhaps encouraging to all of you to know that very famous physicists also make mistakes. The direction that science travels is not a straight line. It often goes this way and then this way and this way. Eventually, progress is made. And even Einstein made serious mistakes along the way. But overall, over this whole century, a major experiment concluded the result of confirming predictions of his theory made in 1915.
La figura anterior mostró los personajes que han contribuido a la detección de las ondas gravitacionales. Esto ha tomado aproximadamente 45 años. No recuerdo todos los nombres, así que vamos a revisar la diapositiva más tarde. Tres personas, bueno, dos están vivas, recibieron el premio Nobel a finales del 2017. Y un consejo que quiere dar a todos, dice que ve muchas personas jóvenes, muchos estudiantes. La moraleja de la historia es que físicos, en física se hacen errores, a veces la física o la teoría no va en una línea recta, puede ir directo o doblar 90 grados. Y recordar que científicos famosos, incluyendo a Einstein, también hacen errores.
So I think this is a good place for us to stop, and thank you very much for your attention this morning. And a special thank you to my good friend Julio Urbina for such a good job of translating for you.
Taylor, por favor, no se retire, que va a haber una ceremonia final, obviamente, que entregar en primer lugar un reconocimiento al doctor Joel Taylor. Por favor, profesor, may you be here? Doctora María Velarde, por favor. Y vamos a convocar a un joven que representa un poco la unión de todos nosotros. En primer lugar al CONCITEC, porque fue el que obtuvo el primer premio en la Feria Nacional de Ciencia y Tecnología en Lima. David Guerra, por favor. David Guerra fue premiado por el CONCITEC como el primer puesto en la sección en la región Lima, en la Feria de Ciencia y Tecnología. Vamos a invitar por favor a la señorita Milagros que entregue el diploma de reconocimiento a David Guerra, quien le va a presentar al profesor Taylor. La foto por favor ahí.
Tiene que abrir. Tiene que abrir.
Muy bien. La doctora León Velarde le va a hacer entrega de la medalla de honor, por favor. Muy bien. Aplausos, por favor. Para la foto de honor invitamos a nuestros